Yeah, welcome dear friends. Today we are going to see topic on static magnetic fields. Static magnetic fields are those in which the magnetic field due to a current carrying conductors will be static in nature. So we are going to learn about the static magnetic fields from the basics from the Biot-Savart's law. Now this is the syllabus in the static magnetic field. The static magnetic field we also call this as electrostatic fields. So in the third unit we are having three basic categories where we have to learn about the magnetostatic fields. The first one about Biot-Savart's law and then Ampere circuit's law. And then the next topic is about the force between the two materials carrying the current, where Lorentz force equation come into picture, and the force equations and the torque due to the magnetic fields we are going to just discuss. And then the last we are going to discuss about the inductance of materials, where inductance of loops, solenoids, and we are going to just see the magnetic boundary conditions at the last. So this is the overall picture of the third unit of electromagnetic fields. So coming to the Biot-Savart's law. Biot-Savart's law, this experiment was analyzed by two scientists. By They are the Jean-Baptiste Biot and Flex Savartz in the year 1820. So on their name, this particular experiment has been named as Biot-Savart's law. So we just go with what is Biot-Savart's law and what the experiment they have did, and what analysis they have just carried on, that we just see in this particular video. In Biot-Savart's law states that the magnetic differential field produced at point P by differential current element ideal is proportional to the product ideal and the sine of the angle alpha between the element and the line joining P to the element, and is inversely proportional to the square of the distance between P and the element. Now this is a statement of Biot-Savart's law. Here what it explains is that we have a current element, the current element which is shown in the blue color. Now this is the current element. This is the current element where the current I is flowing, and due to this current element we have some magnetic field due to this flow of current. So we are, by using this Biot-Savart's law, we can determine the magnetic field due to this particular line current. So how we can do is, we can calculate this particular magnetic field by using this particular Biot-Savart's law. So here, when the DC current is flowing in a current carrying conductor, let I be the current, DC current, then we go and we try to calculate the magnetic field at a particular point of observation. So we have to see the magnetic field at a particular point. So let capital P is the point of observation from which we want to calculate the magnetic field due to the current. Now, so first we try to take this point P, and we just have a representation where we have here a cross mark with a circle around. This is inward to the pitch or into the pitch, because we are calculating the current into the point. So this is the representation to the point P into. And if we have like dot representation, So consider if we just have a point with a circle that is outward the point, right? So that will be the direction outside. Now this is the representation for the into the page we call or inward direction of the magnetic field. Now, this is the point of observation where we are calculating the magnetic field due to this particular current element. Now, when we calculate the magnetic field at this particular point, so what we have to do is we have to take an infinitesimal element of this particular current carrying conductor. So we take the infinitesimal element, so we represent mathematically as dl. So this is the infinitesimal element, and from the infinitesimal element we just draw a vector to the point P. Now this is the point P, right? So we just draw a straight line from the infinitesimal element dl to the point P, and the angle by which, now the angle is important, how the angle has been taken. Now the angle how we take is that the current direction is from the top to bottom and the point is towards the right hand side, so the angle should be in such a way that it should be towards the point, right? So we have, so the angle made due to the current element and the point P is alpha here, right? This is how we take. Now here the magnetic field due to this current element is calculated at a particular point P, where P is the point of observation, and we calculate in such a way that from the infinitesimal element dl we just draw a straight line from dl to P, and that will be the vector we take like r, and the angle made by the line element and the line joining dl and P is alpha. Now coming to Biot-Savart's law, what it states that, so the Biot-Savart's law states that the differential magnetic field produced at point P by the differential current element ideal. So the magnetic field due to the current element ideal. So ideal is the magnetic field due to the infinitesimal element dl, and it is proportional to the product of ideal. So that will be the product of ideal and the sine of the angle alpha. So it will be like ideal into sine alpha. So right, and now the equation will be like this. So the equation 3.1 shows the Biot-Savart's law, that is dH is directly proportional to ideal sine alpha by r square. So in the definition it is in such a way that the differential magnetic field is directly proportional to the product ideal and the sine of the angle alpha between the line joining the element and the point of observation P, and it is inversely proportional to the square of the distance r between the point P and the element. Now equation 3.1 shows the magnetic field, differential magnetic field ideal sine alpha by r square. Now this Biot-Savart's law dH, we can just remove the proportionality constant like k. So here dH equal to k into ideal sine alpha by r square, where k is the proportionality constant and the value of k is 1 by 4 pi. So the equation dH is equal to ideal sine alpha by 4 pi r square. Now this is the Biot-Savart's law in terms of a scalar form. Now if we want to write the Biot-Savart's law in terms of a vector form, now this is the equation 3.4 in terms of the vector form. So how we can write is that, so we have the vector form of the Biot-Savart's law as dH equal to ideal curl ar cap by 4 pi r square. So that means we just take the curl between the current element I and this particular direction r, from that is the direction from the point from the infinitesimal element to the point P. So we take the curl between the two, right? So that will be like ideal curl ar cap by 4 pi r square. So if we just expand AR cap, we know we have a formula where AR cap equal to R bar by modulus of R. So if we just substitute it, we have the differential magnetic field ideal equal to ideal curl R bar by 4 pi R cube. Now this is about the Biot-Savart's law, where I have explained this Biot-Savart's law in terms of the scalar form and in the vector form. Thank you for watching this video, and in the next video we will just go with the another topic of static magnetic fields. Thank you.